with the presentation pose estimation of 3D objects in non-continuous video sequence using evolutionary correlation filters.
Hola a todos, thank you for attending this presentation. I'm very glad to be here. If you didn't know, I'm alumni from Citedi, so I'm very glad to be here again. So my name is Kenya. Have been studying in last 3-4 years. It's about pose estimation. The thing is, I want to talk about optical technique. It's not a common technique for solve this problem. So the title having a video sequence that is non-continuous. What is that? Non-continuous. That is a very impressive video capturing. So it's a challenge over another challenge, and I want to introduce this topic with using a research while study task for imaging applications to obtain descriptors, such as location, orientation, scaling, depth information, or geometric distortions or change of appearance of an object. That is noise, geometrical distortions, light sources for a real scene. So image application is important because we can use three-dimensional information such as object pose tracking, fixture alignment, optical metrology, pose-based games, video games, medical imaging. Actually, recently I'm working with virtual and augmented reality, pose and action analysis for video analytics, and object recognition. So all these topics are important three-dimensional information. That is, real images commonly contain degradations given by noise, challenging conditions like background clutter, motion blur, geometrical changes of the target. All the time the target is changing the appearance, even is distorted, or is an articulate target that is not the same target all the time, or the same appearance all the time in all frames. So we have studied the last many years correlation filters with Dr. Victor Diaz. And correlation filters are very robust. Has been proven that high noisy images. So, and also cluttered scenes like background clutter, and performs very well in this condition. So we want to a hybrid technique. We propose evolutionary correlation filtering for solving pose estimation, and we want to prove it in non-continuous video sequence. In this project, we demonstrate the robustness of the proposed algorithms in challenging image conditions. Most important, the abrupt pose changes of the target observed frame by frame. and actually motion blur with us a challenging condition of not precise video capturing. So a signal that is a frame F, we're going to call F, that is a projection of a 3D scene into a two-dimensional plane. So we have a camera, we have an observer world in a 3D, we live in a 3D world. So in the time when the camera captures a frame, the camera represents this observed world in a two-dimensional signal, right? So this mapping of 3D to two-dimension information or two-dimensional signal, we want a single capture with our with this algorithm. So first, we represent the scene as a model, as a signal. Summarizing is the scene. It contains a target that is embedded in a disjoint background and may contain additive noise. So given this, we have another information that is this letter gamma, capitalized gamma, that involves the appearance modification of the target. That is that this unknown location and is its appearance is an unknown pose. So we built a system with this block diagram using a template matching using correlation filters. That is, we have an input image and we have target templates. These target templates are generated with synthetically with computer graphics, and we build a filter bank, each one with each template given this. In frequency domain, we build a filter bank, and these peaks, correlation peaks, is the measure how the both signals are related. So if the peaks, this peak has some form, it means that the match is very accurate, for example. So we compute the correlation in frequency domain, and each filter in this bank, in this diagram, is given by of that observed scene. In the proposed methodology, we have simple 3 steps. So we initiate the algorithm, and the first step is the observation. The observation is very simple. Is the transformation of 3D to two-dimension images given by the camera, and we initially giving by template matching. This template matching is given by 3 steps: template generation, correlation filtering, and evaluation, and finally a filter back evolution given by the genetic algorithm. In the observation, we represented the pose that we want to estimate as a vector state. In this vector, we have several variables. These 6 variables we want to estimate the pose. Is represented the pose is x, y, the location, scaling s, and 3 rotation parameters. Then in the first frame, as you can see, we have an initiation process consistent on a set of different pose configurations. That is, this vector contains a set of different poses because we want to build a filter with each pose and determines which one have best match. If you can imagine that is a very vast exploring search a search domain of all the combination of pose combinations is be non-continuous. That is, that can perform very badly. It's a very bad video capture, and also is all frames can be kind of scrambled. The frames is not a natural sequence. is the target can be abruptly changed in appearance. So this is the main one. Then the second step is template matching. That is, we want to explore all the best match, but this is very vast. So it's very huge search space. So we use this correlation filter to measure all the match for each one templates we measure, and then we evaluate with a metric that distinguish from a target or of background clutter, for example. And finally, because we don't want to explore all that vast possible of combination of poses, we evolve the filter bank generation. So in order to find the best pose parameters, scaling and rotation parameters of the target. So we make sure that we decide that the filter with the best metric, DC metric, or the best match, is the estimated pose, is associated with the estimated pose of the target. So for experimental results, first we measure with this metric that distinguish the filter detection in this evolution process. So imagine that this is the first frame, and 0 is not good for us. So we're looking for near from 1 to 1. So imagine that in the first frame we have this all blue estimated, that is poses that is very far from the optimal solution. So all these candidates give us, with these algorithms, yields to evolve of the genetic algorithm. Some of these candidate solutions can be near from 0.9, and then as the algorithm can refine with this evolutionary approach. In these other graphics, we can see the evolution in terms of popular size, and in terms of number of generation, the genetic algorithm. This is estimation. And this graphic is the evolution to this metric in terms of signal to noise ratio. So is demonstrated that it's very robust in signal to noise ratio. One in terms of population size, that is the number of filters in the filter bank, and in terms of additive noise with given in noisy frames. So in this row is with different population, and in these graphics we wanted to test how can I how can I measure the abrupt pose changes? So we define an experiment. It's a very simple experiment that is a synthetic video of the target, and we measure from each, and we measure it with the DC metric, the quality of the filter bank. Is clearly that if the degrees of difference is bigger, the quality of the filter will be lower, but we wanted to measure that. 50 degrees in appearance, degrees of rotation angle is a lot in appearance. So it's a good result. Because I say it because we didn't expect that robustness of this technique. The same with location errors and orientation errors. And I have a video here. Okay, let me explain it first. In this video, imagine that it's a video sequence, 400 frames, and we divide it by 4 batches. That is 4 portions or pieces of this sequence, 100 frames. In the interior of this batch, the video, all the video is very imprecise. It's very poor quality video. But in each batch is continuous, but we scramble the order of these batches and try to produce very exaggerate post changes, appearance changes of the target. So is the first batch. The silhouette is traced because we estimate the 3D information of the target. I didn't print the 3D model, but the silhouette marks the estimation. As you can see, it's very scrambled. Commonly, if a tracking algorithm, if lost the target, is kind to search all the scene, or many frames could be lost. But in this approach, we can retain that pose, even if it's a frame. Very good achievement for an optical technique that is being used commonly in 2D applications, and this is used in 3D applications. We can demonstrate that with. So in conclusions, we use this technique. It's an evolutionary correlation filter, and I love challenging conditions in images and try to detect targets with a single camera. We estimate 3D information. So this is an evolutionary approach. We can adapt the correlation filter to find the best match, the best filter, and the algorithm refine itself frame by frame. And these results obtain high accuracy even with the applications, even if not the common application of correlation filters. So this presentation is based on this research article. If you want.
Right now we're going to start a questions and answers session. If anyone have any question.
Okay, hi, do you have an idea of vehicle, car, or with some specific application, like augmented reality or something like that?
Yes, we are working first in autonomous vehicle with target tracking. It's a topic that I work in the last and augmented reality for the same for target tracking or target detection with 3D information, even if you only have 2D input. So this is the main research.
Are you thinking how to implement this camera with a laboratory system, but in the future, like with a car or something like that, you need to embed this some microcontroller, or do you have any idea about this and what are you going to do, or?
Yes, real-time systems, embedded systems, it requires real-time results. So this is the main challenge for circuit, for example. But could be a lot of strategies like parallelism, graphics parallelism, or I don't know. the thing is, we want to evaluate all the conditions before we test it in an embedded system. So.
Have you considered to extend this technique for articulated objects, maybe by combining with machine learning techniques, or have you thinking of that?
Yes, absolutely. Is a very deformated model, if I can say it like that. And I think that requires more sophisticated or hybrid and sophisticated methodology like machine learning, for example.
Color images or grayscale?
No, in this study, just the grayscale information.
Anyone have a question?
To convert the 2D plane to the 3D plane in a real test, more or less.
The time of
processing the algorithm to obtain the results to go to the 2D to the 3D.
of the whole process is quite a lot of time. I didn't have the number here, but it's in seconds. Is very not for real time, not that I wanted, but not all the filters. If you can see in the graphs, not all huge set of filters is required in a real application, because as you can see, if I use 32 filters, maybe can be enough for this test, because the algorithms refine in the generation. So I want to test for good more, so for an experimental and statistical results. So maybe can be reduced with that, and the image size also. I also use a big image size of image. So it can be reduced with these strategies, but right now.
Okay, please join me to congratulate Kenya. Please.